Hi everybody, welcome to the 5.2 notes. These notes are on the extreme value theorem, global versus local extrema, and critical points. So to get right into it, this page is like a little bit of a review problem. And so there's 4 vocabulary words that we're going to use a lot in this unit. That's absolute max and absolute min, and then relative max and relative min. The word absolute can be switched to global and relative can be switched to local, so just look out for those. So we're going to just talk about these. We're going to go across. So just starting off with, let's start off with absolute. So absolute means greatest, right? And so if I look at this graph, this point right here, D, is our absolute maximum point. It's the highest point on the graph. Technically, you can have more than one absolute max, but if you were to have another absolute max, say this was the y value 4, then you would have to have a point that also had the y value of 4. But there's only going to be one point in the sense that there's only going to be one highest y value. So that's the absolute max. This one is the absolute min because it is the lowest point. That is not spelled right. Absolute min because it is the lowest point on the graph. And then we also have relative maximums and mins. So this one right here, B, is a relative maximum because it is relatively higher than the points around it, right? It's like higher than this point, it's higher than this point, so it's considered the relative max. Technically, based on that definition, this point right here is also considered a relative max. It's the relative max and it's an absolute max because it's relatively higher than the ones around it, but it ends up being the highest. And then you probably guessed it, this one's the relative min. Technically, and we'll learn more about this in a couple days, this one's not considered a relative min because we can only see the points from the left side, not the right side, and so we can't classify it as relative min because it's, yes, relatively lower than these points, but we don't know what's going on over here. So that's just a little introduction. So the extreme value theorem says if a function is continuous on the interval a, b, then there is an absolute max and there's an absolute minimum. Abs minimum. So again, that just basically means there's always going to be a tallest point if it's continuous, and there's always going to be a lowest point if it's continuous. And let me give you a little graph sketch right here. So let's say I'm going to draw a continuous function. Okay, so this is my continuous function. It is continuous on the interval a, b. And if you notice, this has a lowest point, it's right here, and then it has also a highest point right here. So I have a guaranteed abs max and absolute min, and that's always going to happen when you have a continuous function, even if your highest and lowest points just end up being an endpoint. So here's a little technical definition on the side. Extreme value theorem. More technical is suppose that f of x is continuous on the interval a, b, so continuous on the interval a, b. Then there are two numbers, a is less than or equal to c, and d is less than or equal to b, so that f of c is an absolute maximum for the function, and f of d is an absolute minimum for the function. So that's the more technical definition, but you just need to know the one I just circled. So let's look real quick, and let's talk about does the intermediate value theorem, the extreme value theorem apply on the interval. So 0 to 6. So 0 starts here, 6 goes here. This one is not, does not apply because it's not continuous at x equals 2. So the answer is no. This next one asks about 0 to 6 as well. So this one also doesn't count because if you guys look back on this definition, it says A, B, and it has a bracket, which means the closed interval. And so these points right here, they actually don't exist here. And so this one is continuous on A, B, this is continuous on 0, 6, but it's not continuous on this. And so as you guys can see also, that means there's not going to be a lowest or highest point. So this answer is no, because not continuous on 0, 6. So here's another vocabulary point. And the extrema always occur at something called a critical point. So extrema, absolute max and mins, always occur at something we call a critical point. So critical points are where the function exists, so aka the domain exists there, so there's no hole in the graph. So the function exists, and there's either two places that you could see a critical point. The derivative equals 0, or the derivative doesn't exist. So that's where there is a critical point. Extrema, so if you ever see extrema, you can automatically say, oh, there's a critical point there. But the way that you identify it algebraically or graphically is that the derivative equals 0 or the derivative will not exist here. So if we look through this like sketch right here at C, if you guys notice, C is an extrema. It's a relative maximum, or actually technically it's the absolute maximum. But if I were to draw a tangent line, which again, the derivative of the tangent line is the derivative, if I draw a tangent line right here, that tangent line has a derivative of 0. So it's an absolute max and its derivative equals 0. Right here is also another extrema. This is an absolute min, this is a relative min, and right here, this is a sharp point, so f of b doesn't exist. And we get to see that it's an extrema. Oh, sorry, this one, f of g doesn't exist, and we get to see that it is an extrema. I wrote one note over here too as well. So if a function has an extrema, they will occur at critical points. So all extrema, anytime you see a relative max, a relative min, etc., there's always going to be an extrema. So if you look at the graph of the derivative, you'll either see that the derivative equals 0 or it doesn't exist. But just because there's a critical point somewhere doesn't mean that there's going to be an extrema there. And we'll see examples of that later. So the concept here is like a square technically fits the rectangle definition, but that just because a square is a rectangle doesn't mean rectangles are squares. So those are just extrema. So we're going to work mostly on critical points today. So example 3 says determine the critical points of the function. So to find critical points, if we're not looking at the graph, we could figure this out by just looking at the graph, but this is our little steps to finding critical points over here. So if you notice, the critical point definition has to do with the derivative. So the first thing we're going to do is we're going to find the derivative. So that's our first step. So I'm going to do that over here. The derivative of 24x squared is 48x plus 48. So that's our first step, is find the derivative. The second step is kind of a mixed one. First is there any place that the derivative does not exist? So does the derivative not exist anywhere? And this, if you guys look at this function, this is just a line, and a line has a domain of negative infinity to infinity. So the answer to this is no, there's nowhere the derivative doesn't exist. So in our step 3 then is we know that it's not going to be a critical point because the derivative doesn't exist, but it could be a critical point because the derivative equals 0 there. So what I'm going to do is I'm going to set it equal to 0. So I'm going to do 0 equals 48x plus 48, and then I'm just going to solve for x. So that's my step 4, solve for x. So I'll subtract 48 on both sides, and I'll get negative 48 equals 48x. I'll divide 48 on both sides, and we'll get negative 1 equals x. And so we have an extrema at negative 1 because f of negative 1 equals 0. And just for fun, let's go look at the graph and look at what it looks like there. So let's find Desmos real quick. So I'm going to show you, kind of try to prove to you that what we did is right. 24x squared. So we're going to look at the original graph because there should be an extrema here. So if I go to negative 1 and scroll down, and if I look at this point right here, there is a critical point here. And if I tap on that point, it's negative 1, negative 24. So we were correct. There was a critical point there, and that critical point represents a relative minimum. Okay, we're going to keep going. So this next one's going to be a little bit more complicated. But the same steps. So we have y equals 8x cubed plus 81x squared minus 42x minus 8. So we'll start by taking the derivative. So we'll get 24x squared plus 162x minus 42. So again, this is a quadratic. The domain exists for all real numbers, so there's not going to be any critical points because the derivative doesn't exist. So we'll go ahead and set it equal to 0, and we'll solve for x. But this is like a little bit of an icky problem, as you guys can see, because this doesn't factor super well. So I'm going to factor it, but if you guys want to use the quadratic formula, you can use that, but just make sure you practice that. So if you want to use the quadratic formula, and we are going to have to use that later, but it's negative b plus or minus the square root of b squared minus 4ac all over 2a, and we are going to have to use that in a second, but right now I'm going to factor. So I'm going to look through these terms. I got 24, 162, and 42. And one thing I always do when I start to factor is make sure that there's not a greatest common factor. And there is a greatest common factor here, and that is 6. So I'm going to pull out 6, and I'll be left with 4x squared plus 27x minus 7. And then now I need to factor that. This one's like this is a harder problem to factor because the a value isn't 1. And so I'm going to use something I call factor by grouping. And so when I do factor by grouping, and again, this is why you might want to just use the quadratic formula if you feel more comfortable. But to factor by grouping, what you do is you do a times c, and that will be negative 28. And then you think about what adds up to negative 28 what multiplies to negative 28 and adds to 27. And in this case, that's going to be a positive 28 and a negative 1. And that will add to 27. And so then I'll write 0 equals 6 times 4x squared plus 28x minus x minus 7. So in this factoring technique, I'm just replacing 27x with this because this is 28x minus x is equivalent to 27x. So I can just substitute that in. And then I will kind of split it into two terms. So I'm going to look at these two terms and think what's the greatest common factor between 48x squared and 28x, and that's 4x. And so left would be x plus 7. And then I do the same thing over here. What's the greatest common factor between negative x and negative 7? That's going to be negative 1. So I'll get negative 1 equals x plus 7. And if I do this factoring technique correctly, these two terms should be the same. So I'll do 0 equals 6. I will pull out the greatest. So we have two terms here. We have this term, and they both have a factor of x plus 7. So I'm going to pull out x plus 7, and that will leave me with 4x and negative x. And that's my factoring technique. So I factored there, and then I just need to solve for x. So I'm going to do x plus 7 equals 0. The 6 gets to go away because that's just a coefficient. 4x minus 1 equals 0. This gives me x equals negative 7, and this gives me x equals 1/4 if I add the 1 over and divide by 4. So either of these places, there is a critical point. And later this week, we'll talk about like how can we tell which kind of critical point it is? How can we tell if it's a minimum or a maximum, etc. Okay, next page. We're only going to do a couple more algebraically, and then we're going to do some with graphs. So example 5. F of x equals 6x to the 5th power plus 33x to the 4th power minus 30x cubed plus 100. So f prime of x equals 30x to the 4th power. This one's actually kind of hard, but it's okay. Plus 33 times 4 minus... You done? Okay, for the sake of time, we're going to skip example 5, and if we have enough time, we're going to come back to it. But here's our next function, f of x equals x divided by x plus 3. So one thing to keep in mind by this problem is it's not a polynomial, it's not quadratic, and it is not like a line. And so the domain actually is a little bit different. So there is one place on this function that the graph doesn't exist, and that would be where you are forced to divide by 0. So if you were to plug in negative 3 here, you would have to divide by 0. And so the domain of this function, and this is going to be important, is all real numbers but x equals negative 3. So this function exists for every place except for x negative 3. You would see a hole in the graph there. And so just keep that in mind. But we're just going to go ahead and take the derivative here. And yes, I know what you're all thinking. Do we need to use the quotient rule? And the answer is yes. So the derivative of the numerator is 1. So you'll do 1 times x plus 3 plus the original numerator times the derivative of the denominator, which is 1, all over x plus 3 squared. And then I'm just going to clean this up. So this is going to simplify to be x plus 3 plus x all over x plus 3 squared, and that equals 2x plus 3. So this is our function simplified. That's the derivative simplified. And so the two questions we ask ourselves is there any place where this derivative does not exist? And actually there is an answer to this one. It would not exist at x equals negative 3. But because the original function doesn't exist at negative 3, that does not count as a critical point, because there couldn't be an extrema on the original function if it didn't exist. And so x equals negative 3 does not count because the original function is also not defined there. So I'm going to write in a list, x equals negative 3 is not a critical point because function f of x is not defined at negative 3. So if it did exist at x equals -3 and then the derivative didn't, it would be considered a critical point because fx is not defined at x equals -3. So that's just like a big note, and that's why I gave you this example. But from there, we're going to solve for x. So we went down the road of, is there a critical point because it does not exist? The answer is no. But now we're going to ask, is there a critical point because is there any place where the derivative equals 0? So to solve this, it looks super tricky, but you're just solving for x. And so to solve for x, I want to get things off the denominator. So I'm going to multiply both sides by x plus 3 squared. And when I do that, these go away, and then also so do these, because anything times 0 is 0. So you have 0 equals 2x plus 3. You'll subtract 3 on both sides, and you'll get -3 equals 2x. And so your answer to this one is -3/2 equals x. So there is a critical point at x equals -3/2. Next problem. So this one's a graph. The question is, this is the graph of f prime of x. So this is the derivative. And it says, for what values does the original function have critical points? And so two conditions again is there any place where the derivative doesn't exist? So as I go from left to right, everything's good, hole in the graph, everything's good. And so if there is a hole in the graph, that means it's not continuous. And if it's not continuous, it is not differentiable. And so there is a critical point on the original function at x equals 4 because f prime of 4 does not exist. And in this situation, we're just assuming that the original function has a domain of at least 0 to 6. And then the other one is, are there any critical points because the derivative equals 0? Well, the derivative equals 0 here, and the derivative equals 0 here because those y values are 0. So there's also a CP at x equals 1 and x equals 3 because f prime of 1 equals 0 and f prime of 3 equals 0. Okay, we're going to keep going. We're going to do this next problem, and we're going to do it graphically and algebraically because the graphic way is actually very helpful. So again, as I look at this function right here, we just need to talk about this, again, is not like a quadratic or a polynomial, and so sometimes the domain is not -∞ to infinity, and something to remember with the square root is that you can't have like a negative of a square root. It doesn't work that way, and so I need to think like, is there any number that I could plug into the square root that would make it negative? And the answer in this one is no, because no matter what number you plug it in, you're squaring it, and then if you square a number, that becomes positive. And so the domain of this one is -∞ to -∞. So we just got to kind of keep that in mind. So from there, we will take the derivative. So to take the derivative of this function, yes, I know what you're all thinking. The chain rule. Yes, we have to use the chain rule. So I'm going to rewrite this function as x squared plus 4 to the 1/2 power. And this is the chain rule. This is the inside function. This is the outside function. So I'll start by taking the derivative of the outside function. So pull down 1/2, leave the inside as it is, and then I do 1/2 minus 1, which is -1/2. So that's the derivative of the outside, and then I have to take the derivative of the inside, which is 2x. And then for all of these, I am going to simplify. It really helps the solving process if you do simplify. So to simplify, to start off, I'm going to write this as a fraction, 1/2. Because this is negative, it moves to the bottom. And then also because it's like 1/2, I can put it back in its square root form. And then this will just be like times 2x, and then these 2's cancel out. So this is my simplified derivative. So that's the derivative. First, is there any place where the derivative doesn't exist? So we can't divide by 0. However, this is never going to get down to 0 because we're at +4, and this would have to equal -4 to get this down to +4. But again, this can't be 0 because it's squared. So there's no places where the derivative's not going to exist. So then we'll go our second method, and we always have to test out both of them. It's not like you can stop if one of them works. But I'll set this equal to 0. And then I'll multiply x squared plus 4 on both sides. That cancels out. This on the left side ends up equaling 0. And so then I get my critical point is 0 equals x. So that one is easy peasy. It doesn't look easy, but like you totally knew how to do it. So now I'm going to walk you through how to do this graphically. And these graphic ones are really helpful when you have like no idea how, well, you actually have to know how to take the derivative, but these ones are helpful graphically if you don't know how to solve. And so we're going to do this one, and we're going to keep in mind that we know the derivative of this is this. So to solve these problems graphically, you still need to know how to find the derivative. But what if you like looked at this problem and you were like, I have no idea how to solve for x. So this is what you can do. It's a little shortcut. So first thing you're going to do is you're going to go to your calculator, and I'm just going to write off steps. I'm going to do it with you, but then I'll come back and write out the steps. But the first thing is under y equals, you're going to plug in your derivative. So let's start there. And I already did it earlier, but under y equals, you're going to plug in your derivative. So that's how it's going to look, just like that. So x divided by the square root of x squared plus 4. So that's your number one step. Your second step, and I'll write these back down in a second, is to go to graph. And this is what my graph looks like. So I have some things popped up here, but ignore them for right now. So this is what my graph looks like. Your windows might look a little different than mine, but one thing that you might notice is that you can kind of tell that it's crossing the x-axis there. This time, it's pretty obvious that it's at 0, but some of the problems that you're going to do, it might cross, like if you look at my cursor, it could cross like right there, and like I have no idea what that number is. And so that's why what we're doing next is really important. So what you're going to do is you're going to press the second button, and you're going to press second trace. Trace is at the top. And that will take you to the calculate button. And then if you look under this calculate settings, if you go down 1, it says 0. So I'm going to press 0. And this 0 button will help you figure out exactly where the zeros are. So exactly where it crosses the x-axis. So what you'll do is you'll take your cursor, and you'll do this more than one time if you have more than one x value. But you'll take your cursor and you'll go a little bit of left of where you see there's a potential x value at 0, or sorry, where there's a x-intercept essentially, and you'll press enter, and you'll go a little right of it, and then you'll press enter, and then I think on your calculator you have to press enter one more time, and you'll get, if you read right here, it says 0 is x equals 0, and so that would be our answer. And that is really helpful, especially when you have like more complicated problems that you don't know how to solve, or like if you have like trig problems that you have no idea how to solve. And so the answer to that one again is x equals 0, so that's what we figured out based on the graph. But I'm going to go ahead and write out the steps. So the first one is you plug in the derivative. Second one is you go to the graph. Third one is you press second trace. Fourth is you press 0. Fifth step is you go left of the 0 and you press enter. Then you go right of the 0 and you press enter twice. And then you have your answer. So that's how you do those ones. I think we have 2 more, so we're going to keep going. But we'll go over how to do these more tomorrow if you guys want some more help with that. Okay, 2 more. So example 11, determine the critical points of the function f of x equals x times ex squared. Okay, let's just get right into it. This one's a little bit trickier. So we're going to go ahead and find the derivative. 2 things you need here: product rule, and you need the chain rule. So it's a very nice problem. So I'll start off, I'm going to highlight my 2 different functions. So this is function 1, and then this is function 2. And within function 2, there's also a little bit of a chain rule right here. So I'll start by taking the derivative of x, which is 1. So I'll have 1 times e to the x squared, and then plus x times, so the outside function is still e to the x squared, but then I have to multiply by the inside function, which is 2x. So that's my derivative. I'm going to set my derivative equal to 0, and I'll get e to the x squared plus, this ends up being 2x squared e to the x squared. And you might have no idea how to proceed here, and I would not blame you. But what I will start out by doing is factoring out e to the x squared, because if you notice, it's in both terms. So I'll do 0 equals e to the x squared. I'll be left with 1 plus 2x squared, and then I'll set both of those equal to 0. So e to the x squared equals 0, and then I'll set 1 plus 2x squared equal to 0. So let's handle the one on the right first. So if I do this, I would subtract 2x squared on both sides. I'd get 1 equals negative 2x squared. I divide both sides by negative 2, and I get negative 1/2 equals x squared. So if you're here, one important quality to know is, again, that you can never square something and get a negative number out. So there's no number that you could square here that would give you a negative number. And so over on the right side over here, there's going to be nothing that you can get out of there. So there's like no solution over here. And then one other thing that you guys probably don't remember, and I do not blame you, but you cannot, e to the x never equals 0. So you can never get this down to 0. And so this also gives you no solution. And this would be a great one to use the calculator for to help you out there. And so this is an example where there are no critical points because there's no solution. No critical points, no solution. So there's no critical points. Okay, one more and then we're almost done. I know that one was kind of trickier. We have one more that's going to be kind of terrible, but we can do it. So this is y equals y squared plus 1 all over y squared minus y minus 6. So again, we have to set equal to, or we first have to take the derivative. So if I take the derivative, I'm going to get 2y times y squared minus, oh, sorry, I keep saying y's. Sometimes I mix my y's and my w's up, but w minus w squared plus 1 times 2w minus 1 all over w squared minus w minus 6. So starting off with the values that could potentially make the derivative undefined. So where could it not exist? So if I could get this to equal 0 down here, and sorry, this should be squared, then my derivative wouldn't exist. But that would be the same numbers that my original function's undefined for, so I don't actually care. So there's nothing I can do there except I can start to solve. But one thing I'm going to do, I'm just going to clean up my derivative before I start solving. So I'm actually, I know that we don't always do this, but I'm going to do some distributing. So 2w times 2w squared is 2w cubed minus 2w squared minus 12w minus 2w cubed minus plus w squared minus 2w plus 1 all over. I know this is terrible, but it's okay. You can do it. Okay. And then these cancel out because they're like terms. And I think that's all that cancels out nicely. So now I'm going to combine like terms. So negative 2w squared plus w squared is negative w squared. And then I'll have minus 14w plus 1 all over w squared minus w minus 6 squared. So that's it cleaned up. Now I'm going to set that equal to 0 so I can solve for it. At this point, you guys might have realized that these denominators just end up canceling out, and that's going to happen here again. So they just cancel out because if you multiply anything by 0, it goes away. So now you have 0 equals negative w squared minus 14w plus 1. So the question is there anything that multiplies, technically this is, you'd have to do like negative 1 times 1. So is there anything that multiplies to negative 1 and adds up to negative 14? The answer to that is no, so we're not going to go with that. So we are going to pull out our handy dandy quadratic formula when that happens. I'm going to write the quadratic formula down here. It's negative b squared plus or minus b squared minus 4ac all over 2a. So if I look at this function right here, the a value is right here. So a equals negative 1. B is the one in front of the, just like the w, so b is negative 14. And then c is 1. And so I'll just plug that into my formula. I have a meeting, so people might be coming in, but I'm going to hopefully try to finish. So it'll be 14 squared because I just made it positive. Oh, wait, sorry, it's negative b. It's not negative b squared. So it's positive 14 plus or minus negative 14 squared minus 4 times negative 1 times 1 all over 2 times negative 1. And because I have to go, I want you to try your best to solve that, but the answer should come out to be x equals negative 14.071 and x equals 14.071. So I hope you get those answers out. I'm sorry for this painful problem, but it is so good for you. Goodbye.